As I understand it, in the standard particle model, um, uh, point particles like the electron don't decompose into anything. They're primitive. Does it also make no sense to ask what strings are made of? They're just primitive.
Yeah, that is a very interesting question, and it ties into something a little bigger, and I think it's the kind of thing you're asking me about. So let me kind of enlarge your question a little bit and then answer it. So, of course, there's been a history in theoretical physics of the so-called reductionist program. So we started out with, fluids and gases, and then we learned that those were made of molecules, and the molecules were made of atoms are made of protons and electrons, and then protons are made of quarks and gluons. And so does this process ever end? So first of all, this was kind of, many people would view this as what the frontiers of theoretical physics are. Understanding the laws of nature at shorter and shorter distances. And some people, indeed in 1985, so in one sense, the answer to your question is no. The string theory can't be made of, strings can't be made of other things, because there are two ways of saying this. One is, if they were made of other things, we'd have to correct the equations somehow. And the consistency of string theory is so exquisitely precise and finicky that we can't modify them in one iota. No other theory in the history of physics was like this. If you take, in quantum field theory, you can have 3 quarks, you can have 5 quarks, you can have neutrinos, more neutrinos, whatever. You can add more stuff. Maybe some stuff you thought wasn't there. In string theory, there's this. It's a kind of an all or nothing proposition. You can't monkey with it. So this could potentially mean, and there's another problem that you would have, is that so we did this computation of the entropy of a black hole using string theory, or in stringy universes, which our own may or may not be one, but at least in some stringy universe, there's some way of making sense of what Hawking did, Bekenstein and Hawking. Now, we got very precise agreement. So you could say what they did was predicted how many gigabytes there are in a black hole. And Vafa and I actually counted them, and they agreed. Now, if the string has more structure, there would be more gigabytes, right? More configurations. And so you'd be in big trouble. So there are many different ways of saying that the answer to your question has to be no. This very different, there was never an argument like this in any other theory that you'd reach some kind of end. And that was, I guess, that was philosophically very interesting. And so many people thought, okay, we've reached the end, and I was not one of them, and I'm not, but many people say, okay, with string theory, has the potential that it's the end of the reductionist program. We learned that, molecules were made of atoms, and atoms made of electrons, protons made of quarks. And finally, we reached the end and we're done. And that wrapping up all of physics is maybe its sight. Now, I had a lot of conversations with Steve Weinberg, probably the most eloquent champion of the reductionist program. That this is what physics is. And somehow, okay, it could be a really wonderful man and a great scientist who sadly passed away last year. And, okay, it could work that way, but it doesn't feel right to me. It seems there's always one mystery begets another mystery. And would we understand everything there is to understand about string theory? There'll be some more questions that we'll have. And there's lots of things left hanging. How did the universe begin? Why are we in 40? There's lots of things left hanging. And so I said to Steve, why do you think we're ever going to find the end? I mean, aren't we just going to have more questions? He says, what would it even mean to know all the laws of physics? That just sounds really strange. And he said, well, that's what they used to say about the Nile. Never going to find the end of the Nile. They explored the Nile. Everybody thought that there was no end to the Nile. It just went on forever. And then finally they found it. That was it, And so we don't know maybe we'll understand everything about physics. That's where the word which I don't like, theory of everything. Could this really be a theory of everything? I don't know. But for now, we're not in trouble. For now, there's lots of stuff we don't understand. Whether it could happen, we don't really know. But there's another important wrinkle in this, independently of that, is while you can't, this was an interesting wrinkle, and it's a good example of how string theory forces you, its equations kind of drag you along and open your mind to different ways of thinking about things. And so what turned out to be, we found is that actually string theories are not the fundamental entity of string theory. They're one of many ways of describing some big structure. So so that there are things that you can do to string theory to make all the strings disappear. And you're left with some other kinds of objects, brains and other kinds of weird objects. And so strings are not fundamental in string theory, and we don't know what is fundamental. It's like, we can start in Boston and describe the road system by giving all the how far you go on each road and how many turns you take to get all the other cities in the United States. But that doesn't mean that Boston is fundamental. We could also start it in Pasadena or Palo Alto or St. Louis or whatever, and that doesn't mean that Boston is the end of the world or the beginning of the world or anything like that. It's just where we started describing from. And strings play that same role. And what is I think, even more profound is even the idea, and this is a little harder to explain, but related to the holographic principle, that somehow the laws of physics, the old way of thinking is somehow the laws of physics are written at short distances where we can't see. And then we work out their consequences for longer distances. Who said that's how it has to be? Maybe it's the opposite. Maybe the laws of physics take their simplest form if you describe them out at infinity and work your way back in. And in fact, we're being led to that kind of thing. So just as we thought we were getting to the end in some sense, of course, we have to get to the end, we also have to do experiments. That's important. The theorists are kind of racing ahead of experiment now because experiments have gotten so difficult and expensive, not because we don't think they're important. But we do what we can, and it looked like there could be sort of an end to the laws of physics in the form of strings, but then it kind of blew up into our face and sent us back to long distances. And who knows, maybe this problem you mentioned an hour ago about the cosmological constant, why is it so small? There are things we don't understand at the biggest distance scales too. And maybe we have to totally reformulate. That's my kind of hope, is that the cosmological constant problem is an indication that there's something we really don't understand about. It's not just short distances we don't understand, but the biggest distances, or we understand the distances we live in. And we have trouble both understanding very short distances and very long distances. And maybe those are somehow related. Okay, I should be saying that's not a podcast. I mean, this is all things I think about late at night. But, but anyway, I don't think we're anywhere near the end. Really, I think we're at the beginning, And,
well, a few things, or at least one thing is that you mentioned Weinberg. He's one of those dream guests that, very unfortunately, I just missed by starting my show a little bit too late. But two things you said that are really important. That one, the theorist is racing ahead of experiments, and the second thing is that the consistency of string theory is so sensitive. As you put it, it's all or nothing. And the work with Vafa you referred to, counting the gigabytes in a black hole, was a huge advance for string theory and is strong evidence for the theories, M theory maybe is what I should say. Right,
so it's very important. Value. If you're in a field, okay, the best thing, of course, is to have an experiment. But if you don't have an experiment, it might be good to just go home and cry. I'm not going to just go home and cry. I'm going to sort of do what I can. And some people will think no problems of this magnitude could be solved without experiment. They might be right, but we're trying. And you don't know what the future of science is going to bring. My view is you don't know what the future of science is going to bring, how it's going to proceed. People use the history of science to justify various approaches and stuff. But again, so many different things have happened that you could. So everybody, I think what it takes is every curious mind looking at the facts before them, thinking about how they can contribute, what they can do. And we just have to blanket all possible approaches and we'll get through eventually. And we don't know where the break is gonna, the break is gonna come.